What is up, you guys? Welcome to another episode. I am thinking of names for this. I'm here with Bart K. One of the names I'm thinking of is Fundamental Health, so you guys can vote down below for names for this series of talks that I'm going to be doing on YouTube and where Bart's going to be sharing on his channel. So today we're going to be talking about vitamin C, antioxidants, oxidation reduction. Do we need vitamin C on a carnivore diet? Are we going to get scurvy? This was Bart's idea, so credit to Bart. Thanks for coming on, Bart. It's always good to hang out with you. How are you today?
I'm good, my man. It's always a pleasure to talk to you as well, Paul, of course. And it's just exciting that we as a carnivore community can share ideas and share the knowledge and share the theories. And look, we're going to talk about a lot of things today that's pretty cutting edge. We're going to be a little bit technical. Sorry about that, boys and girls, but we're going to try and keep it as accessible as possible. We've got some exciting ideas to share with you around where this area looks to us like it's going. We've just spent an hour or so, mapping this out ahead of time. So hopefully it goes according to plan. Yeah.
We are live. Yeah, we're just recording this live, guys. So if we mess up, you're going to see it. We're not going to edit it. Neither of us has time for that. We're just trying to get out good content and share interesting conversations with people in the carnivore space or the keto space or just the health space in general, who are thinking about how to create health. So I love that you suggested this topic, Bart, because one of the questions that I get asked about a lot on podcasts, or I think when we tell people we are eating an animal diet, when we are eating a whole foods animal-based diet, nose to tail, they say, you're gonna get scurvy, right? And so I love disabusing them of this notion. I love the idea that we can really dig into the science and the history and the evidence around vitamin C, otherwise known as ascorbic acid, and get a sense of why we haven't seen a single case of scurvy in people on the carnivore diet. So, I think that, have you seen any cases of scurvy on the carnivore diet?
No, not one.
Do you supplement with vitamin C?
I don't, no.
Neither do I. And I will admit to people that when I started doing a carnivore diet, I was scared of this because nobody wants scurvy. So I actually did supplement with vitamin C in the beginning. And then I read more about it and it was so interesting. And I stopped supplementing with vitamin C a number of months ago and I haven't had any problems with any issue in my body. So let's just talk about it. What is your sense of what is scurvy? What do people see, when they get scurvy?
Okay. So scurvy is a condition that can develop under certain circumstances in humans, and other animals as well, of course, but we're talking about humans here, so let's stay with that. Vitamin C, ascorbic acid, ascorbate, whatever you want to call it, in the human body plays a number of roles, which we're going to talk about today. One of those is antioxidant effect, but another really important one is in the formation of collagen, which is perhaps one of the most important proteins that we synthesize on a day-to-day basis. There's a huge amount of collagen in your body structures, and vitamin C is a cofactor for the formation of that collagen. If you have a level of vitamin C which is too low, and when I would say too low, as it turns out, and it will become clear from this discussion that too low is a lot lower than what the RDI will tell you. But if you get insufficient, truly insufficient vitamin C in your body, you're going to have a problem forming collagen, and that's going to lead to a number of signs and symptoms of breakdown. There's going to be petechial hemorrhaging, which Paul can explain to you. There's going to be slow wound healing. There's going to be sores developing. There's going to be loosening of teeth in the sockets. Basically, random bleeding and all these kind of things are going to be happening. And obviously vitamin C deficiency, scurvy at that level can, if left undealt with, can be fatal. So
yes, exactly. So that's exactly what we see clinically. I should say that the disease of scurvy is essentially unheard of in our society. It's more of a historical disease. It could happen, and it only seems to happen when people are not eating fresh meat. And this gets to the really interesting ideas of how much vitamin C we actually need. And we will address that. And then we will come to questions around how much vitamin C is optimal, because a lot of people are mega dosing vitamin C. And I think that we would both agree that there are some major issues with that. So let me do something real quickly here for people to help them understand what we're talking about. So Bart and I have not done this on a Zoom call yet, but we'll see if we can make this magical. So I'm going to try and do a screen share here for you guys. Hopefully you can see what I'm looking at right now. So on my screen, hopefully this will come up. I'm showing you guys a cartoon showing the way that collagen is made into a triple helix. So collagen starts as a single strand. Collagen is 3 amino acids, which are, as I talked about before, glycine, proline, and hydroxyproline. That is collagen. So one of those is glycine. There's been a lot of interesting discussion recently about methionine and glycine ratios. I would refer you guys to my stuff on Instagram about methionine and glycine ratios. Briefly, I'll just say that I think it's important to make sure we're getting enough glycine in our diets, especially if we're eating a high methionine diet, so that we don't use up the glycine when we buffer excess methionine, because a high methionine diet can cause the body to use glycine to buffer methionine. Glycine is a conditionally essential amino acid, so if we use it all up and we can't make enough, then we will become deficient in glycine, which means we will not be able to make important proteins like collagen and glutathione. We're going to talk about both of those in detail today. So the idea with glycine supplementation, whether in the form of hydrolyzed collagen, gelatin, bone broth, tendons, tendinous tissue, is to make sure you have enough glycine. And it kind of goes back to this idea of eating nose to tail, that we wouldn't just eat the muscle meat. There is some glycine in muscle meat, but it's much higher in connective tissue. So we make collagen from glycine, proline, and hydroxyproline. And then as you can see here on the screen, a single strand of collagen is hydroxylated. And one of the cofactors in this reaction is ascorbic acid, and others are iron, alpha-ketoglutarate, and oxygen. So if we don't have this ascorbic acid, we will not hydroxylate collagen. And then subsequently the collagen strand is glycosylated, and there's a glycogen or a glucose molecule here. The glycosylation is added to the collagen strand, and then it forms a triple helix, which is the actual usable form of collagen in the human body. So if we do not have adequate amounts of vitamin C, we will not make the triple helix of collagen. It's, DNA is a double helix, collagen is a triple helix, and then all of our tissues start to break down. We get, like Bart said, wound healing, bleeding, petechial hemorrhages, all kinds of issues like that. So that is one of the reactions we use vitamin C for. We also use vitamin C in the synthesis of carnitine, and we use it, like Bart was suggesting, as I would say, a water-based, a water-soluble antioxidant. There are various compartments in the human body in which we need to do antioxidant reactions, in which we need to manage the movement of electrons. And in the aqueous, that is the water compartment, vitamin C is one of the molecules we use to do that. Another molecule we use is glutathione. There are also lipid compartments in which we need to manage oxidation reduction reactions. At this point, I just want to pause and explain to people redox and oxidation and reduction, because I think that it's important for people to understand this. It gets talked about so much. It's what runs our bodies. So basically, my take on this, and I'll be curious to see if you think this is a good explanation, Bart, you're welcome to add whatever you'd like. But my take on this is that when I was in general chemistry in college, we learned the acronym LEO, the lion says GER. So loss of electrons is oxidation, gain of electrons is reduction. And it's really as simple as that. Most of life happens with the loss and gain of electrons. And so when we say that a molecule is oxidized, it means it's lost an electron to another molecule. If we say a molecule is reduced, it means that that molecule has accepted an electron from a molecule that is being oxidized. So when there's a redox reaction, reduction and oxidation, there's a transit. It's like a currency transaction. One molecule gives an electron to another molecule. Would you add anything to that, Bart? How do you think we can help people understand redox reactions?
Yeah, it's as you say, it's both very simple and quite complex, and depending on the level that you want to engage with the thing is how you would talk about it. I mean, the LEO, the lion says GER thing is great. I've taught that thing myself for years and years in general chemistry courses. The thing for people that I would say is that the first thing is that it's often confusing that we use the label oxidation, because people then think that necessarily it is involving molecular oxygen. Okay, now that
Right.
is not the case. Not the case at all. The reason that things that are thought of as oxidants are called oxidants is purely because the most powerful oxidant we know about is oxygen. So all these other things are called oxidants. Most of them are not oxygen and have nothing to do with oxygen. So when we're speaking in terms of chemistry, when we talk about oxidation, as Paul rightly said, we are talking about the transfer of electrons from one molecule or one moiety to another one. So the oxidant will donate electrons to the reductant. In so doing, the reductant is oxidized and the oxidant is reduced. So it's a couple, that's why it's called redox. It's a couple thing. You can't have oxidation without reduction. You can't have reduction without oxidation. This basically, to keep it as simple as possible, it's simply, as Paul says, is the transfer of electrons from one thing to another thing.
And that is really the basis of human chemistry. I mean, that is what we run on. I mean, as Bart and I are sitting here talking to each other, we're not aware of this, but as we talked about last week, the movement of electrons, whether it's from a hydrogen molecule to an ATP molecule, or it's happening in our mitochondria, it's happening all over our bodies, especially in the mitochondria. There are free radicals that are produced in cellular respiration. So we essentially talked about the electron transport chain. The movement of electrons through the electron transport chains creates this gradient, this passage, this current of hydrogen ions through the membrane of the mitochondria into the intermitochondrial space. And then those hydrogen ions move out through the ATP motor into the space between the two mitochondrial membranes. And that process creates ATP. In that process, there is an electron at the end that has to go onto an oxygen molecule to form water, and there are free radicals produced. And that is one of the main places that we find what are called reactive oxygen species. Like Bart is saying, not every redox reaction involves oxygen. It's always just the movement of an electron, but oxygen is involved sometimes. And so what our body is doing is having molecular policemen, molecules like vitamin C, vitamin E, glutathione, that are in charge of sort of policing this movement of electrons. And so when we say that vitamin C can be an antioxidant, we mean that vitamin C can either donate or gain an electron to manage some of these free radicals. Does that sound reasonable to you, Bart?
Absolutely, yes, spot on. That's exactly what it's doing, yeah.
Now I'm just gonna share something else here with people. One of the main reactions that our body is trying to control is, let's see if I can get this to work here. Yeah, there it is. Okay.
There we go.
So one of the main reactions that our body is trying to control that involves redox is lipid peroxidation. So what you can see here is that we talked about this a little bit last week, I believe, that when you have an unsaturated lipid over here with a double bond, this is a monounsaturated lipid, but it could be a polyunsaturated lipid if there were more double bonds here. When you have an unsaturated lipid, this double bond is susceptible to electrophilic attack by this. This is a hydroxyl radical right here. This is an OH molecule with an extra electron. So this is a hydroxyl radical. This is essentially a free radical that is going to attack the hydrogen here adjacent to the double bond and form a lipid radical. Again, we're getting kind of technical, but I want people to understand these terms. There's a lipid radical. So here's an electron that gets donated over here to this molecule. So there's an unpaired electron here. It goes to this molecule. It ends up here. You get a lipid radical, right? So that's an oxidation reduction reaction. There's a loss of electrons here in the hydroxyl. There's a gain of electrons here in the unsaturated lipid, and water is produced over here. Well, this is the really bad offender, this lipid radical. And the reason it's a bad thing is because the lipid radical undergoes what is called lipid peroxidation reactions and propagation. And this is what we do not want to have happen in our bodies. This is what creates lipid peroxides down here, which are uniquely damaging to our cells. There are many things which can do this, but you see this lipid radical then forms a lipid peroxyl radical. We're getting into some kind of esoteric chemistry, but an oxygen then is attracted to this free radical over here. You get a lipid peroxyl radical, which combines with an unsaturated lipid, and you get a lipid peroxide. And this is a very, very reactive compound that participates in this propagation reaction and forms more lipid peroxides. This is the type of thing that vitamin C, glutathione, vitamin E, other endogenous antioxidants, but not plant antioxidants, as we've talked about. We have our own antioxidants, are involved in stopping in their tracks. They want to stop lipid peroxidation. Incidentally, I will add here as a caveat that I came across some literature showing that sulforaphane actually induces this process, which is interesting to me because we think of sulforaphane, I talked about this in many of my podcasts, sulforaphane is a very strong oxidant molecule. And many of these oxidant molecules are thought of as hormetics, but ultimately they are toxic. And the reason they are hormetics is because they get into our bodies, they are immediately detoxified, they activate the NRF2 pathway because they are oxidative stress. But in that process, they can induce the same reaction. So people should not believe that sulforaphane itself is doing good things in your body. It may have a hormetic effect by inducing increased glutathione, but the reason it's inducing increased glutathione is because it is creating these lipid peroxides in the human body, right? I've seen literature to suggest that sulforaphane increases the levels of acrolein and 4-HNE, which are oxidized omega-6 fatty acids that are very dangerous in the human body. So sulforaphane, again, highly oxidative stressful molecule. What I've argued in the past is that there are plenty of ways to get adequate glutathione without putting molecules that are toxic in your body. You don't want to get extra 4-HNE. You don't want to get extra acrolein in your body. But this is the kind of stuff that vitamin C and these other antioxidants are doing. Does that make sense?
Yeah, it does. I mean, and also I would sort of add, just for those probably more likely my listeners who aren't aware of hormetic, what that means. Basically, it means that a very small dose of something might induce a positive outcome in the human body on balance. Any more than that is very, very definitely going to cause a toxic effect. So you've got this J-shaped curve, basically. So hormetics are things that induce things that may or may not on balance be shown to be beneficial, exactly like what Paul was talking about there.
Right.
So yeah, absolutely. That's kind of where that one goes, I think. And that leads us nicely to the discussion points around the antioxidant effects and things like that we were talking about.
Yeah. So the other thing I'll add to that discussion about sulforaphane is that as I've spoken about on podcasts, my feeling about sulforaphane, if your listeners haven't heard this, is that it's a net negative, that if we look at it, it may have hormetic effects regarding glutathione production, but it also competes at the level of the thyroid for iodine absorption. So I would argue that overall, these plant compounds, if we just look at them in isolation and we sort of are myopic and we just look at them under the metaphorical street lamp, we'll say, oh, there's benefit here in the human body. But I think we have to look at them as a net benefit. Well, we have to really prove a net benefit in the human body. And I don't believe that sulforaphane is net beneficial. I would argue that it's net toxic. Definitely too much of it can be toxic. That's the J-shaped curve you were talking about. But I would argue that the benefits that we get from sulforaphane from a glutathione standpoint are not unique, and that we can achieve adequate glutathione, optimal glutathione status without sulforaphane or without plant molecules that are oxidatively stressful, which always tend to do other bad things in the human body because our body hasn't seen them before. In the case of sulforaphane, competing with iodine absorption at the level of the thyroid. So okay. I think that's such an interesting piece of the sulforaphane thing.
Awesome. So that just talks to me anyway about being a holistic practitioner, about understanding where things sit in their context within the workings of the human body at large, and talks about, yet another example of why reductionism in science, while a useful tool, is also often used in a way that leads us to folly.
I totally agree. I couldn't agree more. So I think now we'll come to the interesting question that perhaps is on everybody's mind. How much vitamin C do we need on a carnivore diet? Can we get enough from a carnivore diet? Like we both agreed, neither of us is taking vitamin C. Neither of us has taken vitamin C in probably over 14 or 16 or 18 or 24 weeks. So there's an interesting study that I want to talk about. Is it all right if I talk about this one?
Yeah.
So this is such an interesting study. So the name of the study, and it really points to the amount of vitamin C that humans need to function optimally. The study was published in January 2006. I will link to it in the description of this video, and I'll send it to Bart so he can link to it. In fact, actually what I will do is I will screen share.
I was just going to say, you can share it with us right now, Paul.
I will screen share it right with everyone and see if it'll work here. All right, so
there it is.
Medical experiments carried out in Sheffield on conscientious objectors to the military service during the 1939 to 1945 war. So this is a pretty crazy study, right? Like, this would never have been done in our time, but they took conscientious objectors and they basically did the scurvy experiment on them. They call it the vitamin C experiment between 1944 and February 1946. And they had 20 volunteers that took part in the experiment. They were put on a diet that excluded all vitamin C containing foods for 6 weeks, but included a vitamin C supplement of 70 milligrams of ascorbic acid. Then 3 of them were continued on the 70 milligrams of ascorbic acid, 7 on a supplement of 10 milligrams, and 10 were given 0 vitamin C. So what they found was that all 10 of the volunteers deprived of vitamin C developed the signs of scurvy in 6 to 8 months. So that's probably the time frame that people are going to develop scurvy. And what's so interesting is that most people in the carnivore world, there are many people in the carnivore world who have been off of vitamin C for more than 6 to 8 months. So if we were going to see scurvy, we would see it by now. And they say here the symptoms included petechial hemorrhages in the skin, around hair follicles, bleeding of the gums, effusion in the knee joints, just kind of like Bart and I talked about. Now, what's interesting beyond this is that when they gave people back the vitamin C, they found that 10 milligrams of vitamin C, 10 milligrams of ascorbic acid was completely adequate to reverse all of the symptoms of scurvy in these patients within a number of days. So what did they say here? The Sheffield study showed that scurvy could be prevented or cured by daily intake of 10 milligrams of vitamin C. The Iowa group found the same, and I think it reversed it within probably a week of giving that amount of vitamin C. So this is really interesting because the RDA or the RDI for vitamin C, the RDA in the States is 100 milligrams of vitamin C a day. But in this experiment, and we don't know what these other people were eating in general, so they probably were also eating glucose-containing foods. Bart and I will talk about the glucose ascorbate antagonism theory. But even in the setting of a mixed diet, 10 milligrams of vitamin C a day was enough to reverse all of the symptoms of scurvy in these patients. And furthermore, what I just want to point out here is that when they looked at people, this is a quote, no differences were found in the Sheffield study in the Sheffield study, the health of those participants receiving 70 milligrams a day compared to the group receiving 10 milligrams a day. And another study by Jacob could not find biological or physiological markers to indicate a condition of vitamin C deficiency in the absence of signs of clinical scurvy. So I think this is so cool. Isn't that cool? Like, we get so worried about this, and this is sort of the low end, right? We know 10 milligrams a day of vitamin C would be enough to prevent scurvy, and there was no clinical or physiologic evidence of a problem when they cured the scurvy, and there was no difference between 70 and 10. And what do you think about that?
I think that's, to me, that's no surprise based on the sort of study that I've undertaken in the area. I think that, one of the things that people need to understand is that the RDA/RDIs, depending what country you're in, for vitamin C, are not based purely on the prevention of scurvy. The RDI says, here's how much vitamin C we needed to feed a small population, mind, of people to have a certain antioxidant status in those people. It's well known that the amount of vitamin C intake required to prevent scurvy is remarkably low. 10 milligrams even is well in excess of what is actually physiologically required in order to prevent scurvy. I'm just a bit disappointed that study didn't have a look at 1 milligram, for example.
1 milligram of vitamin C.
I think that would have done it too, frankly. And I'll give you my reasoning later if we get to that. But at the end of the day, the RDIs are about the proposed role of vitamin C as an antioxidant.
Right.
It's not purely about preventing scurvy. So I guess what we're getting to with this discussion is, yes, humans absolutely require an amount of vitamin C intake. It is minuscule, and the reason for that is to be able to synthesize collagen effectively
Mm-hmm.
It's nothing to do with antioxidant effect.
Probably
That's
not. I think
that's covered in another way, which we'll get to later in the
yeah.
discussion. But
Yeah, I think you're totally right. And I think that is a pretty, I love that you said that, Bart, because I think that is a pretty disruptive concept, you know, that vitamin C may actually not be the antioxidant that we believe it is, that it might just be, we need the small amount to make collagen and that's it. And like we were talking about and hinting at, and we'll get to that shortly for people, vitamin E, superoxide dismutase, glutathione are probably shouldering the majority of the burden when it comes to antioxidant defense. And then another molecule, another heroic molecule that we'll talk about, which is uric acid. It's like this marauding, interesting molecule. We'll talk about that may also be having some antioxidant effect. So that gets into the idea of our evolving understanding of vitamin C. I just want to note for people, have you seen studies on how much vitamin C is in meat, Bart?
I have, and I don't have them at my fingertips right now, Paul, so please don't quote me on these figures, but I believe that if you were looking for 10 milligrams of vitamin C, you could probably get that from a pound of most muscle meats.
I think that, yeah, I think it might even be a little bit less than a pound of muscle meat. So,
yeah.
And then if you're eating organ meat, so let's just think about this from people eating a carnivore diet, you know, 3 ounces of liver has 30 milligrams of vitamin C. So 1 ounce of liver probably has 10 milligrams of vitamin C. You know, yeah, I mean, a small amount of liver has 10 milligrams of vitamin C. And so if you're eating a half a pound of muscle meat and an ounce of liver a day, you're probably getting plenty of vitamin C. If you're eating, I mean, you know, if you're eating more than a pound of muscle meat a day that's fresh, I mean, it can even be cooked. It doesn't have to be completely raw. You know, it can be cooked, but hopefully not overcooked. You're going to get enough vitamin C in a day. And then, you know, if you're eating any liver, you're probably getting enough vitamin C. And then there are other foods that also have vitamin C from the animal. I've talked about salmon roe has a little bit of vitamin C. The brain, the pancreas, the adrenals, these are pretty rare for most people to get. But if you were eating those foods, then you would get a lot of vitamin C. Basically, the point that we are making here for people is that on a carnivorous diet, it's very easy to meet your adequate requirements for vitamin C. And if what Bart and I are proposing is true, there's probably not a whole lot of benefit to going much above that. And then the corollary question, which I think will be interesting to address now, if it's okay with you, is can people get too much vitamin C? Because I've seen this in my clinical practice. I just saw a guy last night taking 3 grams of vitamin C. Actually, it was this morning. He was taking 3 grams of vitamin C. Most vitamin C supplements on the market right now are a gram. So 1,000 milligrams. And that's like, people are just saying like, oh, it's water soluble. It's totally safe. Take as much as you want. But I think that you and I both might have some objections to that. And I think that the question becomes, is there a potential harm taking too much vitamin C? What do you think, Bart?
Yeah, I mean, there are definitely, in my mind, a couple of contraindications or potential contraindications. One is that if you take a shit ton of vitamin C, which, you know, 1,000 times your requirement is a shit ton in my mind, there is a risk that vitamin C can become itself oxidized. One of the oxidized forms of vitamin C is oxalate, boys and girls, oxalate. And then that can become precipitate out with calcium, mainly calcium, but in fact any of the metallic ions, and cause crystals and cause damage and cause inflammation and cause stones and cause all sorts of havoc all around your body. So that's just one potential contraindication, is the real risk that you're going to subject yourself to an acute load of oxalate, which you're not going to be able to excrete effectively.
Right.
There's just one.
I've also seen, I was reading some papers prior to this talk, and so I was surprised to remember, I didn't remember this from medical school, but one of the things I found in some of the papers was that, I mean, people may know this, if people have taken, you know, megadoses of vitamin C, which I would say anything more than 100 milligrams of vitamin C is a megadose. So 1,000 milligrams is definitely a megadose. 5 grams is a big megadose, you know, and some people are taking 10 grams of vitamin C a day. The big doses of vitamin C definitely cause diarrhea. They can cause nausea, abdominal bloating, and heartburn. So something is happening in the gut, whether it's an osmotic effect or the formation of excess vitamin C in the gut to a bad product, or the vitamin C becoming oxidized it has many forms. So one of the breakdown forms of vitamin C is oxalate. Vitamin C can be oxidized to dehydroascorbic acid. So vitamin C is ascorbic acid and dehydroascorbic acid. So I'm wondering if the oxidized form of vitamin C, when you put excess vitamin C in the gut, if the vitamin C actually gets oxidized and the dehydroascorbic acid is directly toxic to the gut. But clearly, if people are getting nausea, diarrhea, bloating, and heartburn, it may actually be directly caustic to the gut membranes. There's also evidence that vitamin C, like you mentioned, increases the risk of forming kidney stones, probably because excess vitamin C in the human body leads to oxalate. And then when we excrete oxalate in the kidneys, depending how well we're excreting oxalate, that can form calcium oxalate kidney stones. Big doses of vitamin C may also lead to the development of B12 deficiency. That was something I don't even think I learned that in medical school. I know metformin can lead to B12 deficiency, but large doses of vitamin C can lead to B12 deficiency. Most carnivores are getting so much vitamin B12, but a lot of vitamin C, because the ascorbic acid, it's an oxidatively reactive compound. And the theory is that it actually can convert by B12 into the biologically inactive analog. So cobalamin has multiple redox states itself. Vitamin B12 is cobalamin. It can be hydroxycobalamin, methylcobalamin. And if you look at like the folate cycle, one of the roles for the enzymes MTR and MTRR is to reduce B12 between different redox states of B12. But B12, cobalamin, when it gets reduced or oxidized, can be more or less effective. It has an inactive analog. So taking a bunch of vitamin C can then do all these extra redox reactions in the body that we don't want to happen. And then perhaps the most interesting side effect of vitamin C, which I want to point out to people, is that in patients or individuals with glucose 6-phosphate dehydrogenase deficiency, it can actually have a hemolytic effect. So I'll do a screen share here and show people this. But this is really interesting, and it ties into some of my disdain for legumes. So I'll move this over here. All right, so if you look on the side of the screen over here, this is happening in erythrocytes, and this is happening in red blood cells. There's an enzyme called G6PD, glucose 6-phosphate dehydrogenase. And the idea is that in red blood cells, the only way we can reduce glutathione right here is by NADPH. Well, the only way we can form NADPH is by taking glucose 6-phosphate to this intermediate here, which has a huge name, 6-phosphoglucono delta lactone, okay? But this is G6PD. This is the G6PD deficiency. Now, if people had an inborn error of metabolism where G6PD is completely inactive, they probably would not even live. So people with glucose 6-phosphate dehydrogenase deficiency have a lower activity. They have a lower ability to make this conversion between glucose 6-phosphate and 6-phosphoglucono delta lactone. Now, why is this a problem? Because if you can't make that conversion, you can't make NADPH, and you cannot regenerate reduced glutathione in the red blood cell. Now, why do we need reduced glutathione in the red blood cell? Well, to take care of organic hydroperoxides right here, meaning when there are lipid peroxides or other peroxide free radical molecules, these are the free radical molecules over here. If we can't take care of these with glutathione, there's going to be so much oxidative damage in this red blood cell that it's going to burst, and we get what is called hemolytic anemia. Why is this interesting to me? Because we know that in people who have G6PD deficiency, they cannot eat fava beans, right? Have you heard of this? So they're broad beans, fava beans, have so many of these oxidatively stressful compounds that are frankly toxic. Vicinine, divicinine, convicinine, isoramyl. They're all toxic compounds in fava beans. And I would argue that there are many compounds which are in fava beans or other legumes that are just frankly toxic. Like plants hate us, right? They do not want you to be eaten. Fava beans are toxic to humans. People with normal G6PD can detoxify those things a little bit, but when you eat fava beans, you are putting in these oxidatively stressful compounds in your body. And also, when you eat sulforaphane, you are putting oxidatively stressful compounds in your body. And if your body cannot do that reaction in red blood cells, you will generate you will use up all your glutathione. The oxidative molecule will be there, whether it's sulforaphane or one of these toxic compounds from fava beans or other toxic compounds from plants, and you will get hemolytic anemia. I thought that was so interesting. And so what we're seeing here, to me, the idea that excess vitamin C taken orally can create hemolytic anemia is crazy, because it means that vitamin C is actually acting as a pro-oxidant when it gets to be those high levels. Does that make sense? I mean, that's the way I think about it.
Yeah, absolutely.
Right.
Yeah.
So what
Absolutely.
we see here is that the body has this delicate balance. I love this concept. The body has this delicate balance. And when we try and muck it up and take mega doses of vitamins, then we are just getting into all these problems with, excess. The excess vitamin C can turn into an oxidant. So I would argue, and Bart, you can let me know if you agree with this, I would argue that when we take excess vitamin C, we are harming ourselves, that we are creating excess oxalates, we are oxidizing B12, we are giving ourselves GI distress, or potentially disrupting the GI membranes. I know the Paleomedicina group has argued that vitamin C may actually cause leaky gut in high amounts. And the form of ascorbic acid that you're taking in a supplement is probably not the way it's going to be packaged in a food, in a food molecule. And then I would argue that it's probably excess vitamin C, at least in the red blood cell, with this mechanism of G6PD, looks like it could be a pro-oxidant, which is not what we want. So it's so interesting, because 99% of the people on the internet would tell you, take all the vitamin C you can. It's the best thing ever. I mean, this was Linus Pauling's thing, man, right?
Yeah. And that would be a mistake. That would be wrong in my humble opinion, and clearly in yours as well, Paul. I agree with absolutely everything you've said. And to kind of reinforce it from another angle, let's bring in a Mendelian inference. For those that don't know, a Mendelian inference is about the genes, what's going on with the genes, etc. Now, some 60 million years ago or so, the human species entirely lost the ability to synthesize vitamin C in our bodies. Okay. Now, obviously that started with a random mutation that was selected for. So we need to take that concept a step further and go, well, okay, it's not just that some people developed this change whereby those particular people can't make vitamin C, and others that made vitamin C continue to live long and happy lives doing that as well. The fact is, no human being, none, has the ability to synthesize their own vitamin C. That means that gene was not just drifting away, it was knocked out. It was selected against. There was a good reason why we needed to get rid of that gene, to get rid of making this substance. The reason, in my mind, is quite simple. Firstly, we can get perfectly sufficient vitamin C from eating animals, which is what we were doing mostly at the time that this ability to generate our own vitamin C was selected against, when it was knocked out of the human lineage. So we could get all the vitamin C we need there. And secondly, there was a parallel development whereby we lost another enzyme, which is involved in the breakdown of uric acid. Now, what that meant was that human beings have a much higher level of urate, or uric acid, if you like, in their bodies than basically just about any other mammal, certainly any of the mammals that can generate their own vitamin C. And that leads us to a discussion of, well, why is that so? Why did we have a gene which meant that we maintained uric acid? Uric acid is universally thought of as a negative thing, as a problem. Too much uric acid causes gout, is what we're told. Okay. Well, what's interesting, and what ties back into what you were saying just a few minutes ago, Paul, actually, it looks like gout only occurs in people who have both high uric acid and low glutathione as well.
So interesting. That's so interesting.
It's fascinating, isn't it? And I just saw this morning, and we discussed this before we started this chat, and I flicked you the stuff, Paul, and you said, oh, give me 15 minutes extra time to read it. And, and rightly so, because it's fascinating. And there is clear inference from another study that we'll talk about soon, where there is a clear linkage between glutathione reduction oxidation and an intermediate step involving uric acid as the scavenger for radical oxygen species, free radicals, ROS, oxidizers, those things that cause oxidative damage. And so it looks very much like the human species has developed an ability to retain more uric acid and that uric acid is playing the antioxidant role that is proposed to be the domain of vitamin C.
I think this is such a cool concept. What a wild concept. I love it. So is it okay if I get a little background about uric acid and
please,
gout?
yeah, absolutely. Yes, go for your life.
So I did a YouTube video about this. If people are curious, I did a video entitled on my channel called "Will Eating a Lot of Meat Cause Gout?" The long and the short of it was no. Let's see if I can let me pull this up really quickly. I'll see if I can do a screen share, and we can maybe talk a little bit about uric acid and the synthesis of uric acid and how this all might play into the equation. So the idea here is that uric acid is a substance that is a breakdown product of purines in the human body. That is purine bases of DNA. So when we eat lots of meat, we are getting purine molecules, and uric acid is a breakdown product of this. But what I talked about in that YouTube video was that generally eating a lot of meat itself will not raise the body's levels of uric acid, that the body can regulate the amount of uric acid in the body by how much is excreted in the kidneys. And so we have a very tight control over the amount of uric acid in our bodies. And I think that, as Bart is suggesting, within modern medicine, we see uric acid as mainly a bad guy, but I think it may actually be potentially beneficial in many ways. And when things go awry, when it's dysregulated, it can be a problem. So what I talked about in that video was that people who get gout clearly do have higher levels of uric acid, but the gout is not about excess purines in the human diet. It's about decreased ability to excrete uric acid when your body wants to. And that comes from fructose, insulin resistance, and alcohol. I talked about all those things. So I challenged people to check their uric acid to see how their gout does in the absence of fructose, in the absence of insulin resistance on a low carbohydrate and non-inflamed diet. Insulin resistance is caused by many things, not just carbohydrates, and then by no alcohol. And if you look at people with gout, they always have one of those three things. They always have fructose in their diet, which we know probably causes some insulin resistance and causes satiety effects by messing up leptin signaling. And then there's also these issues with the alcohol definitely inhibits the body's ability to get rid of uric acid in the kidney. And then the third thing we have fructose, and then the third thing is insulin resistance. Insulin resistance changes the way the body gets rid of uric acid. But like Bart is suggesting, there may be this interplay between high uric acid and low glutathione. So it's only when potentially the uric acid is oxidized, because I have clinically seen people who have high uric acid and don't have gout, or I've seen people with the same level of uric acid, some have gout, some don't. So we're talking, when in my uric acid was about 4.1, and who knows what that means. But in the video, I made the suggestion, the hypothesis that, hey, I'm eating 2 to 3 pounds of meat a day. My uric acid is 4.1. My body can get rid of it as much as it wants. But I think most people in Western medicine would take this very simplistic approach and say, oh, you're eating 3 pounds of meat, your uric acid is going to be 16. What we generally see is that people who are eating lots of fructose end up with too much uric acid. But that aside, I've seen people with uric acid levels of 8 who don't have gout, and people with uric acid levels of 8 who have gout. And so it's not the only thing. And it's oversimplistic model to say that it's simply a crystallization reaction based on a concentration in the joints or the tissues. There's got to be something else going on. I love this idea that it may have to do with reduction in oxidation and glutathione, like we talked about. But it's a complex molecular signal. So I love this idea that humans may actually be using uric acid as a beneficial molecule in their bodies.
And in support of that, Paul, is another finding, another bit of reading I was doing this morning to get a gauge on this. The normal, healthy human functioning kidney will reabsorb and recycle 90% of the uric acid that is filtered through those kidneys. Okay. Yeah. Now, if uric acid is a waste product that needs to be excreted and is a problem, we need to get rid of it. Number one, why is the gene that breaks it down to something further downstream knocked out in humans? And why are we recycling 90% of it? It's not a waste product, is it? End of discussion.
Doesn't sound like it. Let me see. Let's do a screen share here. I'll see. I bet you've seen this paper, Bart. Have you seen this one from Bruce Ames? I'm sure you've seen this one.
Yeah, yes, yep. That's the one that led me to suggest this topic to you, Paul.
Yeah, so the title of this paper, as you guys can see, is Uric Acid Provides an Antioxidant Defense in Human Against Oxidant and Radical Causing Aging and Cancer. It's a hypothesis. Again, it's a hypothesis. It's from Bruce Ames in 1981. And as I've highlighted here, they show in this experimental model that uric acid can act in the same way as vitamin C as an antioxidant, meaning uric acid can serve the same roles in terms of dealing with lipid peroxidation as vitamin C and other antioxidants in the erythrocyte. And I thought that was just so interesting. People can look that up. But they hypothesized even then that perhaps uric acid was serving an antioxidant role. And then we found this paper. You were aware of this before we got on the call, Bart, but I found this paper as we were talking. And there's another one. So this is an interesting one here.
Yeah.
So why don't you tell us what you think is going on in this one? Uric acid and glutathione levels during short-term whole body cold exposure.
Yeah. So what these authors have done is they've done a study with some folks who have got into some very, very cold water, which causes an effect on the function of the mitochondria in those individuals. The effect is that it reduces the redox potential of those mitochondria, which leads to an inflammatory type response and also leads to the generation of an oxidative stress situation where you have too many oxidants, not enough reducers, and so you have a pro-oxidant, pro-tissue damage, basically a bad situation going on there. Now, the body obviously reacts to that oxidative challenge by using its supply, if you like, or its store of antioxidants to neutralize those reactive oxygen species, neutralize that damage. And there's a suite of antioxidants that we've got in our body, and they are sort of stacked one on the other in terms of importance, in terms of activation energies and which ones are used first, and how the pool is depleted in a quite controlled, quite set way. It's something that we don't know as much about as we'd like to. There's ongoing work there to this day in that area. There are many substances acting as antioxidants in that cascade of events that we weren't even aware of, or thought about or taught about in medical school or wherever we studied. For example, uric acid turns out to be one of these. This paper speaks to it in a kind of roundabout way. This is a hypothesis, but what they did is they subjected these people to very cold water, huge dose of oxidative stress, and then they've measured the glutathione and also the uric acid situations pre and post. And what you've got is this highly correlated reduction in both glutathione, which is the master antioxidant, that's seen as the head of the tree, but also there's a reduction in the uric acid concentration, suggesting that the uric acid is acting as an electron donor in that cascade of events, and that then that uric acid is actually interacting with something else, or indeed directly with the glutathione at the head of the tree, and that's reducing the glutathione. So what it's suggesting is, hey, we've got a mechanistically tied series of events going on here. Thus, this is some early indication, sure, and hypothetical, sure, but it says, hey, look, it looks pretty clear that, like we've just seen the mechanistic studies in vitro that Paul was talking about with with uric acid acting clearly as an antioxidant. We've seen the biochemical reactions in test tubes in the lab. This is a real thing. This is happening. And now in a whole working human subjected to oxidative stress and cold water, bam, look, here's both uric acid and glutathione being reduced in parallel. You take from that what you will.
It's pretty cool. It's pretty cool. I'll just do another screen share here and show people what we're talking about in the paper. So I'm going to use the highlighter here. You can see the results of the study. It says uric acid levels measured 1 hour before the winter swimming were 310, which is the range of normal uric acid concentrations. And they say 1 hour following whole body cold stimulus, the uric acid levels were found to be only half of the initial values. However, 24 hours after the winter swimming, plasma uric acid levels were back to the initial values. So this is what Bart is talking about, this idea that, and I think this is so cool, Bart. I was getting so excited when you were talking about this because I made this connection in my head that this is an example of hormesis without using a sulforaphane molecule. So basically, we know that heat and cold stress can induce oxidative stress in the human body. We don't need sulforaphane to do this. We don't need resveratrol to do this. We don't need plant molecules to induce oxidative stress. We do not need molecular hormetic molecules from plants. But this is exactly what sulforaphane is doing. Sulforaphane is an oxidative stress, just like the cold stress is. Now, again, without beating a dead sulforaphane horse, I am just beating the shit out of sulforaphane.
Yeah.
Like, this is the idea that we don't need sulforaphane to do this. And the thing is that a cold stress is a much more evolutionarily consistent hormetic stress than sulforaphane because it doesn't have the other dangerous side effects. It doesn't compete with iodine at the level of the thyroid, et cetera, right? So when people would argue that plant molecules are necessary for antioxidant defense, I would say that is not true. That is bullshit because we can get all the oxidative stress we need through exercise, cold, heat, and sun. We don't need plant molecules to have these hormetic effects. Does that make sense?
And add to that, uric acid is now, I think we can put squarely in the category of things that are clearly antioxidants, and that comes from meat, largely.
It definitely can. So I'll just show people a few of these graphs here. People are welcome to look up that study as well. I'm just like a kid in a candy store. I figured out a new thing.
While you're talking about that, Paul, also the other one while I'm thinking about it that we were going to talk about was this finding that I saw a paper where sure it was rabbits and rats and that kind of stuff, and we can talk about external validity till the cows come home, or the rabbits or the rats, whatever, but there was an effect whereby what they did was injected these animals with uric acid in high concentrations, more than you're going to get from food, by the way, but whatever. And what they've found is a toxic effect on the islets of Langerhans in the pancreas of these animals. It's destroyed those cells. You've got necrosis of those cells. You've got an induced type 1 diabetes from high levels of uric acid. Unless those animals also had adequate glutathione levels. If those animals had adequate glutathione levels, that toxic effect was completely abolished. Isn't that interesting?
That's super interesting. So we could hypothesize that uric acid is a molecule that is oxidatively reactive, and that if you over-inject uric acid, you will get oxidative stress, almost like vitamin C.
Yep.
But if there are adequate molecules which control the redox state of uric acid, namely glutathione, that it can abrogate or it can abolish that phenomenon. That's interesting.
Yeah, completely abolished it. None of the animals that had adequate glutathione levels had an induced type 1 diabetes necrosis of those cells in the pancreas. All of the animals that they subjected to a diet that was depleted in the amino acids required for glutathione production, every one of them got type 1 diabetes out of an injection of the acid, basically.
But wait, Bart, which amino acids are required for glutathione?
Oh, let me think for a moment. Would that be glutamine, glycine, and cysteine, perhaps?
Glycine, right?
Glycine, there you go.
If we don't get enough glycine, or we don't make enough glycine, or we use up all of our glycine, we are risking inadequate glutathione. So perhaps this is coming back full circle now, and people are asking, oh man, I want to make sure I have enough glutathione. How do you make sure you have enough glutathione? Well, you make sure you get enough glycine, you make sure you get enough glutamine, and you make sure you get enough cysteine. Glutamine and cysteine are plenty present in meat. Glycine is more present in the muscle meat. So here we go, methionine, glycine balance, the importance of eating, you know, of the connective tissue of the animal. So that is that. And I mean, we are risking inadequate collagen, which is also made from glycine, and we are risking inadequate glutathione. So I'll just do a screen share here, and I will show a couple of these figures. So this is a figure showing, this is glutathione, this is reduced glutathione, and GSSG is oxidized glutathione. So you can see here, this is reduced. The gray bar is the total of reduced and oxidized. And you can see that in the initial group, then they go in the cold lake, and it is decreased. Both total and oxidized are decreased after 60 minutes. And they don't have a graph, unfortunately, of the actual uric acid, but this is essentially the same thing here. They are showing levels of GSSG, which is oxidized glutathione, now in the white, and oxidized glutathione plus reduced glutathione here in the black, and they are showing initial. And then afterwards, you are getting changes in both of those when you get the winter swimmers, okay? So it's so interesting that, as we are suggesting here, probably what happened was that the uric acid may have served some of the role as an antioxidant, and then, because the uric acid went down in people who did this, and then the glutathione came in and then had to reduce the oxidized uric acid. So again, this is the oxidation reduction. We're transiting electrons and we're moving them around, right? So uric acid may in fact be a part of this equation. And I think this concept of uric acid being an antioxidant is not completely radical. But as we are seeing, we know uric acid can build up to pathologic levels. It can cause gout, but it probably has to do with our overall antioxidant status. And I will just highlight again for people, I think this study is so cool because it shows that you can get a response in your overall glutathione levels. You can get increased glutathione levels after you get oxidative stress. That's a hormetic effect, and that oxidative stress doesn't have to be a shitty molecule like sulforaphane, which is going to do other bad things. It can just be cold exposure or even heat or exercise will do this to the human body. So we don't need plant molecules to obtain hormetic effects in the antioxidant front. I think that's so cool, and I love how it comes full circle. So what do you think, Bart? I think we can maybe wrap it up here. Anything else you want to talk about?
No, look, that's everything on my notes that we discussed prior to that we wanted to go. I think it's gone really well, actually, Paul. I think we've covered everything with some degree of clarity around the thought processes. I hope that people found it accessible. If not, please do contact Paul or myself for further discussions. I'm sure that we can spare some time for that. I certainly can. Don't forget, to those of you who are my people who are not sub to Paul, make sure you go and sub to Paul, because, as I say, his channel is a treasure trove of information.
Thank you.
I think it's a great thing that we can look at these hypotheses and go, look, this is how it looks like things might be working. Here are some of the holes in the reductionist science that we've had rammed down our throats for 50, 60, 70 years. Isn't it great that we didn't know everything and that we still don't know everything? The caveat for all of this discussion is this is two guys who are intellectuals, who are trained in this kind of stuff, sort of shooting the breeze, cogitating on some ideas. We've talked about hypotheses. We've shown some mechanistic data that supports the idea, or seems to support the idea. What we want to do is stimulate further discussion and further research in the area, obviously. So please don't take anything in this discussion as some kind of gospel. It's the shared experience of some research that we've both been reading this morning prior to this chat. Hey, this would be a cool study. Yeah, and we were just like a couple of kids in a candy store throwing this stuff around for about an hour before we came online. So that's the caveat. Take it with some caution. Obviously, take it as hypotheses. Look into this for yourselves. Read these papers. Think about this chat. Watch it several times. Sub to Paul's channel. And if you're not sub to my channel and you're Paul's people, I'd appreciate your support as well, of course.
Definitely my people. If people are following me, they should check out Bart's channel. He's debating Garth Davis. He's got tons of good stuff over there. He was disciplining Frank Tufano and many other things. And so go check out Bart's channel. Absolutely, for sure.
Sure.
So I think what I will say in summary, I didn't mean to interrupt you, or did you have any
No,
other
I'm
thoughts?
finished. That was my summary.
Yeah. What I would say in summary to people is don't worry about scurvy on a carnivore diet. Don't believe the hype that you need a bunch of vitamin C. Don't take mega doses of vitamin C. Don't even take a vitamin C supplement. Just eat fresh meat, eat some liver. You're going to get plenty of vitamin C in your diet. There's no clinical evidence that more vitamin C is going to be beneficial. There's definitely mechanistic data that excess vitamin C, whether it's from a supplement or tons and tons of oranges, could create problems for people. Don't eat fava beans. Know if you're G6PD. Vitamin C, I think, it's this specter in the carnivore world, but hopefully we've, thrown open the doors and been like, we're not as afraid of you. We're not going to get scurvy. Those of us who have done testing on ourselves appear to have very ideal antioxidant status. I've looked at my glutathione levels. I've looked at 8-hydroxy-2-deoxyguanosine. I've looked at lipid peroxides. They all look fine on a carnivore diet. Don't appear to be deficient in vitamin C or any other indicators of antioxidant stress. So people should not worry about this. And the other thing I would say is I actually dissuade people, and I recommend my clients that they avoid vitamin C supplements. I have concerns they may be causing irritation of the gut. And like we're saying, you can get plenty from food. And then we rolled into this discussion about uric acid and antioxidants, making sure you have all the things you need to make glutathione, get your glycine, get methionine, glycine, and eat nose to tail. Eat your organ meats, eat your connective tissue, and start thriving. I was going to say, Bart, you look younger today. I think that every time you and I come on this podcast, hopefully we're just going to be aging backwards, like Sean Baker says.
So. Yeah. I turned 47 on the weekend, so there you go.
Well, happy birthday.
Thank you. I'm now 47 years of age. There you go.
That's amazing. So thank you guys for watching. Check out Bart's channel. Anywhere else people can find you, Bart? Are you on Twitter or Instagram a little bit?
I'm on Twitter a little bit, Instagram even less. You can find me on Patreon, and that is Bart_K. There are a number of different tiers there that you can support me on Patreon from $1 a month, which is basically a donation for which I'll give you nothing except my eternal thanks. There's a $10 tier where you get access to a whole bunch of videos on technical aspects of things that are not available to my YouTube subscribers. And there's a $50 tier where you can have me for 2 hours a month of consultancy on any appropriate topic that I am remotely expert in, which is nutrition, physiology, general health status, cardiovascular physiology, some pharmacologically based stuff, statistics, research methods, any of that kind of stuff. So $25 an hour to steal. I'm absolutely
ridiculous.
I'm ripping myself off, but it's available, and it'll be available as long as I've got time to do it. So go and fill me up with $50 subscribers right now. That would be really
anybody that doesn't pay Bart $50 for 2 hours of his time a month is crazy. That's ridiculous. That's insane.
And I need you to, because I've just shelled out $4,000 on a new PC system.
People know me. They can find me on Instagram at Paul Saladino MD. They can email me directly at paulsaladinomd@gmail.com. I'm a functional medicine doctor. I work with clients. Privately, they can find me at my website, which is paulsaladinomd.com. They can email me at paulsaladinomd@gmail.com. I'm on Twitter at MD Saladino. I have a Patreon too. And I've got a YouTube channel, which is Paul Saladino MD. So Bart, I love this. Let's keep doing it, man. But if you guys are still watching, thank you. Vote below. If you guys do topics below, Bart and I will look at those and decide what video we're going to do next. Maybe if we really like you and your topic gets upvoted, we will do that one, but we will reserve the right to choose another topic. But I'm pretty sure you guys are going to see way more videos from Bart and me in the near future. So stay tuned. Thanks for watching, guys. Thanks for coming on, Bart.
Pleasure. Appreciate you.
All right.
Thanks.